Strange changeable weather that we've been having, kind of weird between, t-shirt weather and heavy jacket weather, so come with a shirt and a jacket and just work the thing out. There's going to be a certain amount of redundancy here between this lecture and the next, which I really should have combined into 2 lectures and put in more about the use of main memory, but we'll go through it, and I'll try to avoid too much duplication. Just as a reminder, since we didn't finish lecture 8 last time, notation, which is different from that in the book. For a relation, I just write pages with a subscript of the relation for the number of pages in that relation. Tuples per page is going to be just TPP for R. The book's notation is useless as far as I'm concerned. And the number of tuples in R is going to be the cardinality of R. And of course, the cardinality, the number of tuples in R, is just the number of pages multiplied by the tuples per page. And that, of course, assumes that there's no free space sitting on top of the pages. So this is one way of doing costing that we're going to be using for the algorithms we look at. And these days, there's a lot more that ends up happening using memory and NUMA rather than assuming things are read from disk, which they were in the System R days, but typically you're going to have everything sitting in main memory most of the time now with the way things are done. So in particular, and so these numbers are going to be things that show up a lot, so I'll remind you of them just quickly. Sailors has 500 pages with 80 tuples per page, so 500 times 80 is 40,000 tuples sitting on top of a page. Reserves is going to be a table that has 1,000 pages with 100 tuples per page. There are going to be 100,000 tuples that are sitting on a page. We started off as a straw horse, looking very quickly at a simple nested loop join, and this is how we define Cartesian product in 180. We're going to look through every tuple in R, we're going to look through every tuple in S, and then, if there's a match, then we're going to put the result of RS in the result. The join column of R is RI, the join column of S is SJ. That's a pretty dumb way of actually doing it. We can get better. That's really expensive. You'd have to go through basically touching every page, 1,000 pages are in R to get the tuples on each page, and then for each of the 100,000 tuples inside R, you're going to be touching every single page inside S, and that really is a dreadful algorithm. There's an algorithm, and I want to emphasize this is the page-oriented nested loop join. It is different from the block nested loop join, which I'll remind you about, we talked about last time. And that's cleverer, just saying for each page that you have inside R, we're going to look at each page, we'll loop through every page that we have in S, and basically on each page, we'll look at each tuple in R, on each page of R, and then we have a page of S, we'll look through all the tuples on that page of S, but you only have to end up touching the pages of S once per page of R. So we have to loop through the pages of R, and for each page of R, we're going to be looking at each page of S. So it's pages of R plus pages of R times pages of S, which is a lot better. And of course, it's symmetric. We could have S on the outside instead of having R on the outside, and that would actually reduce the cost by 500. So that would be better. And we started getting a little bit smarter, actually quite a bit smarter, and using what's called an index nested loop join. And in that one, what you're going to do is loop through all the tuples in R, actually just touching each page of R once. And then you've got an index. Assume that you've got an index on S, where you can find, if you have a tuple R, then you can find all the things where Ri equals Sj by using the index to find the matching Sj's. You have your hands on a tuple inside R, and you of course know what the join column in R is, what the value of Ri is. And then what you're going to do is look at the matching tuples in S by saying, okay, Sj has to equal Ri. I know that the value has to equal 17. I'm only going to get the tuples where the Sj value is 17. And if I have an index on S, I can just get those tuples directly. So it's going to be, the cost is going to be looping through all the tuples of R, which we're going to do by looping through all the pages of R. So that's the pages of R. And now what we're going to do for every tuple in R, that's cardinality of R, we're going to see what we can do about finding the matching S tuples, and we'll have an estimate of what that cost is. And the assumption here, you know, and again, you'll have to work with whatever the real assumptions are in your own environment, is that looking to find the matching S's is going to be about 1.2. Here we're doing IOs without the compute cost. If you're operating with a hash table, and it's going to be between 2 and 4 if you have a B tree. And you know, the actual cost of finding the matching S tuples depends on what's going on, whether you have a clustered index, if it's a B tree or not. If it's a clustered index, it's just going to be 1 IO to get to the actual data that you have in the leaf pages. And in the case of an unclustered index, it may be 1 IO for each matching S tuple. With a clustered index, because the data is stored, then you know it's really going to be whatever number of pages it takes to get to the actual tuples that you have in the leaves, assuming that the non-leaf parts of the B tree are sitting in memory. So anyway, those are just rough estimates. And now we got to another interesting algorithm that we talked about. And again, don't confuse, this is the block nested loop join as opposed to the page-by-page join that we talked about. And this gets interesting, and it's going to be particularly interesting to think about when we get to hash join, which is in the next lecture, which really should have been combined with this. One of these days I'll actually do that. And block nested loop join is starting to be a little bit more clever about how we're going to go about doing this, and we'll take a look at what the costing is for this. What we're going to do is we're going to do, and we can have shadow pages for this, as we had when we talked about how we deal with some of the sorting algorithms. But just to keep it simple, to start with, we're going to assume that we have B buffers, and we're going to use one of them for a special purpose, which is a single buffer from S. Again, we could get cleverer about that. We're going to use another one of these buffers for our output. That's going to be an output buffer. And what we're going to do is we're going to take the other B-2 buffers, and we're going to use them, and we're going to put blocks from R, approximately B-2 blocks from R, into a hash table. And the hash table is going to have the tuples of R, but what we're going to be hashing by is what are we hashing by? The join column of R sub I. So inside the hash table, we'll hash based on R sub I. And we won't really be able to fit B-2 pages inside something that says B-2, because there is a little bit of overhead for the hash table, but I'll just oversimplify and act as if we could put B-2 inside, but it's not really right. So we have a hash table that allows us easily, if we have a single tuple of S, to find the matching things in R for those B-2 pages. Because what we're going to do is we'll take a individual tuple of S, and we get its S sub j. How do we find the matching R sub i's? Not for all of R, but just for the B-2 blocks that we've got in the hash table. We hash S sub j. We find the matching things inside the hash table. Now, if we have matching things inside the hash table, then we've got a join. So that's all nice and pretty. And so we have brought in a buffer of S. We're going to do what I just described for every single tuple on that page, that one page that we have with S. We find all the matches, and we put them into the output buffer. And when the output buffer gets full, we'll write out the output buffer, and then we'll have a free output buffer. And when we're done processing that block of S, we'll go to the next block of S, and the next block of S, and so on, using that same hash table. So we will iterate through all the blocks of S using the hash table. When we're finished with S, we're not done yet, because we can only put actually a little less than B-2 of the pages from R into the hash table. But we'll get the next B-2 blocks of R and stick them in a hash table. And go through the same thing, going through every block inside S. And then another B-2 blocks of R, and then another B-2 blocks of R. And if these things are lined up sequentially, reading in the blocks of R, it's going to be something where you can just do it with one big sequential read, potentially, as you're reading the blocks. And of course, you will have to take the time to construct the hash table, because they're not written out in memory as if it's a hash table. They're not written out on disk as if it's a hash table. And when we're done, we've written everything out to disk with, going through all the different collections of B-2 pages of R. And again, for each of them, you're looking through all of that, so you get the whole result. Now again, we can do several clever things. We can prefetch so that we have, we waste a buffer for another block of S, so we don't have to wait to get the next block of S. We can waste another buffer to have a separate buffer for the output, so we don't have to wait for the output to complete. But you get the general idea of what's going on. So basically, you're gonna go through a B-2 blocks of R approximately, go through all the blocks of S, find the matches, where there are matches, write them out into the output buffer, and when you're done, you have everything that's matched together. So just as a fast comment on the analysis, which you didn't say last time, then I'll take the question. You're gonna be looping, you're gonna be reading in every block of R once. Because you're reading them in collections of B-2, every block of R gets read in once. How many times does every block of S get written in? Once for every B-2 blocks of R that you read in. So it's basically, you only have to go through the blocks of S. You're gonna go through it multiple times, but basically you take the size of R, the number of pages in it, divide that by B-2, and that's the number of times you go through it. Question?
What happens if your output buffer fills up before you finish reading in all the data? Do you just
You write it out.
Okay.
Same nonsense trick that we used when we were sorting. So the two answers. Number one, you write it out and you wait until the write is completed. Number two, you have a shadow block, as we discussed with sorting, where you go ahead and you write out the block that's full, but in the meantime you're filling up that other block.
Gotcha.
So that same thing we did before. Same techniques get used, variations. Okay, and then we ended, and we were very fast about this, but we're going to be going over numbers and costing in this next lecture. So the next lecture is sort of this one, but with more stuff about costs involved in it. And the idea of a sort merge join, and it has some stuff, with remember we looked at doing a sort using merge sort. Do not confuse the sort merge join with a merge sort. They have a lot in common, but they're not the same. The point of a sort is to take the whole data and sort it with divide and conquer. The idea of the sort merge join is you want to be able to join the tables together. And what we'll do is we'll sort them, which means that we can find matches as we iterate through each of them, always advancing whichever one is smaller until we find ties, in which case, and all pairs that are ties will end up being output. So first, take the time using the sort algorithm we've already seen to sort R and sort S. They are now sorted. Wonderful. Isn't it good that we learned how to sort before we did this? So R and S are now sorted. And now what we're going to do is we're going to have a traffic cop on R. We're going to have nothing to do with B-tree traffic cops. I just like the term. We have a traffic cop on R. We have a traffic cop on S. And the traffic cop says, oh, we're going to advance whichever one is smaller until we get a tie. This is smaller, we'll advance it. That's smaller now, we'll advance it. When we get a tie, all the matches that we have found get output. There might be 5 tuples in R that match 12 tuples in S. We'll output 60 tuples. So for this R tuple, there are 12 things. For this R tuple, there are 12 things. For all of the 5 R tuples that have the same value, 98 inside the join field, we'll output the 12 tuples that match it in the S field, right? So, 5 times 12 things end up getting output if, the R tuples have value 98 and the S tuples have 98, and that's the join column. So at that point, now that you've found all the matches, you advance past the matches, and you do the same thing. If one of them is smaller than the other, you advance the smaller one, because the smaller one doesn't have any matches. And then when you hit ties again, do the same thing again. Take all the pairs of ties where the R join column equals the S join column, and you output them. Okay, and that's how the thing works. You resume scanning, and then when one of them gets done, well, that's it. You're finished. You're not going to find any matches for the other if you run out of things in the first. So basically, the idea is you can think of this as going through R once. For each R tuple, when you find a match, you're going to scan through the block of matching S tuples and output all of them. The R tuple together with all the matching S tuples. But there might be other R tuples
that have the same matches in all the things in S. And so, there is a good chance in all except really skewed situations that the S tuples that you want to find will still be in the buffer because you just looked at them. So, you have the R tuple, you have, let's say, even 100 R tuples end up matching, 200 S tuples. Those 200 S tuples, the pages of them, because remember, it's pages, you already sorted. You don't have to jump around to find the S tuples. They're consecutive in the sorted version of S. So you're going to find those 200 S tuples in consecutive pages that are almost certainly still inside the buffer. Why did I say except in a skewed situation? The worst situation, and this gives you terrible results all the time, there's not too much you can do about it, is if you have big R and big S and all the joint columns match each other, in which case the number of things that you'll have in the result, you have basically cardinality of R tuples in R, you have cardinality of S tuples in S. How many tuples do you have in the result? Cardinality of R times cardinality of S, if everything matches everything. Which, by the way, tells you that you could have a huge number of tuples in the result, much bigger than what you had in R and S. In general, you could have 0 tuples in the result, but you could have cardinality of R times cardinality of S in the result, or any value in between. Okay, so now we're going to go past. Questions on that? The merge sort is something that we spent about a minute and a half on, the last 90 seconds of last lecture. But the concept, if you understand about sorting, is pretty straightforward. Again, traffic cops advance and the thing that's smaller, outputting everything where there's tons. Now, System R, which again was built around 1976 to 1981, 82, is a very old optimizer. A lot of its principles are still used. I'll point to several optimization papers, old optimization papers that you can read, including a system that a fellow by the name of Götz Greffi, who got his PhD at Wisconsin, and he was at Microsoft and HP, and he's now at Google. He's done a lot of really good work, a lot of good stuff that he did in optimizers in the good days. He's also the person who wrote those for the last 3 of the 5-minute rule papers that I pointed you to. So I'm mentioning Götz not quite as often as Jim Gray, but mentioning him a lot. Again, very, very good guy. But it's one of the most widely used approaches for optimizer. Götz's volcano approach, which is terrible to read in his original paper, much better in the computing surveys paper that I reference at the end of this lecture as a coda. It's a widely used approach. It works pretty well for small numbers of joins, but as I've mentioned in both courses, I've seen 18-way joins, including a fair number of left or right outer joins as part of that. And I'm serious, from a well-known company that I won't mention the name of, but it's not unusual. Sometimes you have a lot of joins because you write queries using views, and sometimes you can eliminate some of those joins and simplify. Because views make it easier to be able to write queries. But often you may not need all those joins when you join the views back together. A fast story for you. In the early days of System R, there were studies that were done. It's late enough that it's okay for mentioning the company. When System R started out, the first 2 industrial studies were done with the drug company Upjohn and with Boeing. That's been in the news recently with some issues with the 737 MAX, but that wasn't true back in the late 1970s. And basically System R could handle up to 8-way joins. And the feeling was everybody's going to do 2 or 3-way joins. There might be somebody doing 4-way joins. Nobody's going to do more than that. Remember, this was in early days of relation. There weren't any industrial studies done before that. The only other system that was out there in these early days was Stonebraker's Ingress at Berkeley. Almost immediately when the thing was out there, people were not only doing 8-way joins, they wanted more. Reason? Views. Views make it easier for you to encapsulate, to describe something which might be something you want to reuse, something where you can build recursively, queries on top of other queries, the wonderful composition capabilities that are out there. And it wasn't, in some cases, they could have written the query as a 4-way join, but it was just easier for them to write it using the concept of the views of what was there. Again, it was important in the product versions to have more than A-way joins very, very early on. So the general idea of what's happening here, the statistics are not kept completely up to date, even in modern optimizers. It's not worth it, not even in memory. Because it would be too much work to keeping track of the statistics. You remember, even with NUMA jumping all over the place and changing statistics would be a lot of work. So, what happens is that the statistics are updated either when the system feels bored and has nothing better to do. Or it may be updated when somebody says update statistics, or it may be that you have it set so that it's updated, every hour or every 2 days, or maybe the statistics are updated when the plans start, looking considerably worse than they had recently. There are all sorts of reasons these days why all kinds of statistics, and there are lots of statistics that are kept, may end up being updated. And then there are cost formulas. As you'll soon see, the cost formulas are slightly bizarre. They were in the System R days. They're a lot better now. But again, they're based on imprecise statistics, and you don't know how many matches there'll be. I just got through telling you, could be when you join R and S, you have 0 in the result. It could be you have cardinality of R times cardinality of S in the result. Now put this together with, and there's another predicate on R, and there's a predicate times S, and now it's an 18-way join. So you're taking, the 16-way join and combining it with another table. How many things were there in the 16-way join? And how many matches you're going to find in this other table? Scratch, 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 scratch. There are things that can be done based on that. Often the same query is used a lot, and it may be that you can, when you're feeling bored, you can gather statistics and you can learn about what the good plans are. So we're going to be talking, except in a coda that I have later, about how things worked in the old days. But there's lots of new stuff that's done now to end up improving this and get better costing in various cases. By the way, you have to be careful. If you can get really good costs in one subcase and you have really bad costs in another subcases, people can end up getting surprised. And I'll give you a principle that, it's true in general, though I first learned about it in detail at SAP. It's better to give people results all the time in about 200 milliseconds than to sometimes give the results in 50 milliseconds and sometimes in 1 second or 2 seconds. Why? Because nobody notices the difference between 200 milliseconds and 50 seconds or 300 milliseconds. As long as you can give a result back in 200 to 300 milliseconds, people are happy. But people do notice 2 seconds. And so really what you want to be able to do is to have people know what things are going to take approximately and meet those expectations and not surprise them. So avoiding surprises ends up being really important. Now the plan space, even when we start looking at 3- and 4-way joins, gets combinatorially explosive. The number of different plans you can have, even with just a few indexes, and even 4-way joins, ends up being huge in terms of which tables you access first, what join methods you use to deal with them, what access paths you use to get with them, when you do your sorts, or hashing to eliminate duplicates, various ways of doing group by. The space is huge, even these days. And so, okay, there's enough compute power now that you can probably do a reasonable job looking at all the costs, even with 4-way, but again, as I mentioned, there are even 18-way things, so you have to use heuristics to be able to cut things down. System R did something that is not done today. It takes, remember we talked about hunchbacked approaches with B trees. It takes a left-leaning tree approach. Modern, we're talking about left-leaning plans versus bushy plans. Again, that's not a political reference either on the left or the Bush part. We'll be talking about the different ways that you can define plans. System R looked only at the left-deep plans. And the idea is that you pipeline, you get to a table, you take the results of that table, you pipeline down to the next operation that you want to use. So you don't have to store temporary results as you go unless you really want to as part of a plan. So this allows this pipelining thing. For everything I get from this table, I'm going to find all the matches in that table, and then I'm going to find all the matches in that table. And if I have indexes that find all the matches in the next table as I go along, that can be really good. Again, we'll see a lot of examples of that. System R and most other systems try really, really hard to avoid Cartesian products. What's a Cartesian product? I've got two tables, maybe the result of A, B, C, and now I have to decide, do I next join in D, E, or F? If I've got a predicate between A, B, C, and E, I prefer to do that rather than combining with, say, F or D, where there's no predicate involved, because if there's a predicate involved, I'm limiting what shows up in the result. I want to take the things from the previous things that match based on some join column. Whereas if I take the Cartesian product, I really am taking the Cartesian of my left result times the cardinality of my left result times the cardinality of my right result. That gets big. So remember, I said it could be cardinality of R times cardinality of S. If there's no predicate between the two, it's gonna be cardinality of R times cardinality of S. That gets kind of big kind of quickly and probably isn't what I want to do. So you try to avoid Cartesian products as much as possible. So there's information inside these catalogs that you're dealing with in Project 2, which you weren't asked to do in Project 2. There are things where you typically keep track of how many tuples you have, and again, it's an approximate result. It might have been updated yesterday. How many tuples there are in the table, approximately? How many pages there are inside the table? How many distinct values you have in each index, which will help you understand how many matches there are when you're using the index on average. How many pages there are in the index. For things like the height of the index and what the low key values are for each pre-index. You also might keep track of the smallest value even when there isn't an index and the biggest value, so you can assume something about the distribution. You can say if the values are between 0 and 100, then if it's uniform distribution, then everybody got 1/101st of the values on average for each individual value. Of course, if it's a test score, you hope that it's not uniformly distributed and people do better than that. And actually keeping track of histograms, which we're going to get to, is something that every modern database system does in one way or another. Again, there's a lot of detailed statistics that are kept. So all of that's going on. So again, the statistics are inaccurate, old, imprecise, and they won't have the full detail about, there's no way you can figure out exactly how many matches there are going to be between A and B in general, right? I mean, it's hard to keep track of all of the stuff. There are some formulas that we'll be talking about where you'll ask me to justify them, and hell, I couldn't justify them then, and I certainly can't justify them now, but it's hard, this is a hard area. Okay, so there are two things that we keep track of, and maybe somebody can tell me why I'm keeping track of both of them. One of them is obvious, the other is less obvious, but not hard, especially given what I've already said. One of the things that you're going to do, you're going to be figuring out a plan, and you're going to say, here's my best way of getting A, B, C, and now here's my best way of also getting A, B, C, D. But I'll also figure out how to get ABC by first computing, BAD. I hope BAD isn't bad, but, and then adding C and all the rest of it. There are lots of ways I can get ABCD and then E and so on. So there are lots of ways of doing things. So I'm going to figure out estimated costs of doing each operation. And so that's going to depend, of course, on the cardinalities, what comes in, and how many matches you find. And we'll talk about ways of estimating the cost. But there's a second thing that we keep track of, which is the estimated size that you get for your result after the operation, okay, which you're going to figure out based on the size of the inputs and things about your predicates, which are, again, totally, in some cases, unreasonable assumptions. We'll talk a little bit about how those assumptions have been made better. Why am I keeping track of both cost and size? Everybody should be able to answer that. I'll call on you if nobody else. Why does size matter? Go for it.
Because like you said before, with the Cartesian products, the size can rapidly grow.
And even if
you're looking for savings, you're looking for the plan that gives you the smallest size so that you could further down the line further optimize.
I am looking to not have huge sizes, but it's even more direct than that. If the cost of doing a join between X and Y depends on the size of X and the size of Y, I want to, if X was gotten by taking ABC and joining them together, I care about the size of ABC because that'll affect the cost of combining A, B, C with D using some join predicate. So I care about the size that I get for A, B, C, because even if I'm not multiplying together and getting the full cardinality, because I've got a join predicate between something in A, B, C, and D, maybe multiple things. The size of A, B, C is going to affect, if joining A and B depends on the cost of A and the size of A and the size of B. Joining A, B, C, and D depends on the cost size of A, B, C, and then D. So I'll be figuring out costs as we go, because that will end up contributing to the answer. So how do you figure out size estimation? Again, here's an old way of doing it, and we'll talk more about some aspects of histograms. There are some totally unreasonable assumptions here. Try to deal with this in the general case, and you'll be banging your head against the wall. It gets very hard when you have general predicates. But we'll assume here that you've got a query block, which might correspond to a subquery, or you've got selecting some attributes or expressions from a list of relations where you've got a conjunction of terms. Term 1 is true, term 2 all the way up to, that's term K over there. Okay, so basically there's going to be the notion of a reduction factor that shows up here. The maximum number of tuples in the result is going to be what you would get if you took the Cartesian product of all the relations. The cardinality of all the relations in the relation list. That's the biggest that you could get. That would be true if it was just where true, right? That's the biggest you would get, or if all the terms ended up being true. Now there's this notion of a reduction factor. Each term ends up reducing the size by something or other. So basically, for example, suppose that you had something where for gender, where we'll go to a case where you have binary genders, not true anymore, but if you just had male and female, and if you assume uniform distribution, then half the people would be male, half the people would be female in that case. So that you'd have a reduction factor of 1/2, because you have two different values, and if you assume that each of them appears half the time, then your reduction factor would be 1/2. So each term would have a reduction factor. Suppose that you had 50 states that people could be from, and you're looking for something where the state is California or Hawaii. Then the reduction factor would be 1/25 if you assume that all states are the same. Suppose that there are ages between 0 and 100, and you're looking, let me make it easy. Let's suppose it's between 0 and 99 as an age, and I'm looking for all the people who are in the 90s. Then the reduction factor would be 1/10, because there are 100 different values, 0 to 99, and the 90s would be 1/10 of those. There are 10 values that are in the 90s, there are 100 values between 0 and 99. The reduction factor would be 10 out of 100, 1/10, if you assume uniformity. Uniformity is not necessarily true. There are more people at UC Santa Cruz, California, than there are from Wisconsin, for that matter, Hawaii. Uniformity is not necessarily true. But there's another unreasonable assumption here. Maybe somebody can tell me what it is. I'm going to be taking these reduction factors and I'm going to be multiplying them together. So if I wanted to have everybody who's in the 90s and is from California, I take my reduction factor for in the 90s, which is 1/10, and I take my reduction for California, which is 1/50th, and I'd multiply those together to get the reduction factor for the conjunction of the two terms. What other unreasonable assumption am I making? Go.
I think you're assuming that they're all independent of each other.
Independence. Of course, lots of people in the 90s go to Florida. Fewer people these days in the 90s are staying in California, maybe some of them, if I remember. But it's assuming that age and state are independent of each other. It might be true. Hard to keep track of how independent they are of each other, but it's an assumption. Now, when you can't make any better assumption, this is what System R did. And again, there are systems that keep track for frequently used combinations of terms, better idea of what the actual reduction factor would be for the conjunction of the terms. But let me warn you about this. Every time I have a different plan for an 18-way query, I can have all kinds of different combinations of predicates that have been applied inside the result through. And so even just the number of different combinations of predicate to consider combinatorially huge, ugly, wonderful, full employment for overwork optimizer people who, you know, again, get everybody unhappy with them when they improve things for almost everybody, but not everybody. It's a tough thing to be able to deal with. A lot of interesting work in this area for cardinality. So there is the implicit assumption, site even says so, that things are uniform and that things are independent, and we'll say a little bit more about this when we, you know, go later in, but it's a tough thing to deal with. Okay, so we're gonna go through an example, and, you know, again, a combination of this slide, this lecture and the next one. So we're gonna be looking at a number of different ways of doing the joins. We've talked about, again, I will emphasize, we looked at the nested tuple-oriented way, we looked at the nested page way of doing it, we looked at the block way, which played with that hashing thing to be able to do it, which was the block nested loop join, we looked at the index nested loop join, we looked at the merge join. There are lots of different ways of doing joins, and again, next lecture we will also get to that kind of join, which is again another really good one. System R, by the way, only had a version of the block nested loop join, and nested loop join and the merge join. Hash join came later, and it's very good. So here's a simple query. We're going to be looking at, for the name of, you know, looking across reserves and sailors, where the sailor's rating is greater than 5, and the sailor reserved boat 100. So again, the query basically says, give me the names of sailors whose rating is more than 5, and who reserved the boat whose number is 100. And BID, we don't have a separate boats table. We just have, you know, R&S, sailors and reserves. And so you can, you know, I told you in 180 that relational algebra relates to how query plans are done. It's not a perfect mapping, but for our discussion, we're actually going to be looking at things from a relational algebra standpoint to begin with. So we have, you know, the join between reserves and sailors where we're matching two SID values. And then we could go ahead and look for things where the sigma, where the boat is 100 and the rating of the sailor is greater than 5, and then all we want in the result is a projection based on S name. And this is going to be a really super plan to be able to do it. In the case of the block nested loop join, what we could do is go ahead and again join these two things together, and then on the fly, as tuples come out, this is the pipeline, as tuples come out of the block nested loop join, we could pipeline to this predicate where we're doing the sigma of BID equals 100, grading greater than 5. So rather than writing out the result to, you know, to disk or whatever, or even, you know, putting it all in memory and then waiting for the result to be finished, every time we have a tuple that comes out, we can apply the predicates in that sigma and then only project out what we care about in the answer, and that would give us the result. And that would be something that we can go ahead and do. And the cost of this, remember I said briefly to you that what is the block nested loop join? It's going to go through all the tuples inside the left-hand side relation, which might be the sailors. So, you know, we're going to do that. That's the 500 for sailors. And then for basically what we're going to be doing is, you know, potentially looping through all the things inside reserves. And again, by playing it with blocks, we can